Okay, we'll continue and then still have some ground to cover. So, how do we check those assumptions? I've listed those assumptions. And many of them you can check visually, and again, it's making plots and looking at what's in the plot. So linearity. So mostly before you've done that, you've started looking at scatter plots between your independent variables and your dependent variables. And by now, you should know how to make a scatter plot, and you're hoping that it's a linear type of relationship. And if that doesn't help, then you should consider transforming your data or fitting the function which fits better. So if it's parabolic, then you can do the x times to the power 2 plus x, and then you fit that type of function if it's a parabola. You can fit cubic functions or other functions also to which might fit a bit better. Normality, so again, you could, for example, rely on the output which you also got from the residuals, but you could also look at a plot of the distributions, and that would be a QQ plot which you might have come across, and we want all the things to be nice on the line, and that would point to us that it's quite normally distributed. Homoscedasticity, you know the basic things of how to do, for example, Levi's test. So you can in principle use Levi's test, but for more complex models you won't be able to do that because it has many different variables, or you have to run many different of those analyses. So there's something called the Breusch-Pagan test, but you can also again check graphically. And what we want to see here is that there's no funnel in the errors. So basically that bands sort of stay constant, and there's no funnel going that way or funnel going the other way, which means that we'll be underestimating dramatically on one side or the other side of the spectrum of the fitted values. So it's basically looking at whether there's a larger spread across one side of the line than the other side of the line. And independence, you can't really do a graphical test for that. Actually, you can, but it's quite complex. So most of the time, you would use Durbin-Watson test or something called a box-Young test. You might have heard of a Durbin-Watson test. Have you heard of that? But you might have heard of a box-Young test. That's mostly used, for example, when people have time series data and want to see if their data is correctly detrended. But I'll show you how that works. So usually it's a good idea to plot things for the start, and I'll just do that for education. Again, a whole bunch of code, but it's the same thing we've done before. Again, pay attention to what I've done here. I've used the geom jitter type thing, and I've split it out here. It still overruns slightly. It's very, very annoying. I can't tell you why, but there's something in my code which occasionally makes it run outside of the box. So even I can't fix certain things sometimes, but it's overrunning slightly. And here I've said this is the scale. These are the limits of the scale. You can add breaks, as you've seen before with the command. We can add limits for the continuous variable, and that's because it's education, 6 years to 18 years. So assuming that most people will have had 6 years of primary school, that's why I picked for 6. And again, you use pretty breaks. We can add the labels for prestige and education. You can make more complex labels sometimes, which I haven't done now. You would put between brackets prestige, score, education, year, so people can directly see what the result is. I didn't put a title. You can add a title to it, but I did put in a lowest function, and that we're hoping that's a locally weighted estimate and as you see, that can be going all sorts of ways, and it's trying to fit the best possible regression line it can using the nearest points. And so we're hoping that that will sort of look like a line, and that we won't get like an entire parabola, because then we run into problems. And again, I used a team, tufted team, because I think it's quite clean. And so this is sort of what it looks like. So I've used jitters to make sure that the points don't overlap. And you have some confidence bands which tell you the uncertainty around that fitted line. It's not wholly linear, but it's not going in a complete U or a complete parabola. So I'm fairly happy with that. I'm not sure if you would be, but I think this is still acceptable in terms of what it would look at. You could perhaps see that you might be tempted, there's things called broken sticks regression or symmetric regression, to say there's a breakpoint here, and then it goes slightly steeper there. But that's something you can do as a follow-up type of analysis to see if this is a breakpoint, an inflection point, or suddenly it starts matting a whole lot more, so that it doesn't really matter between 6 and let's say 10 or 11. But once you cross that every single year of study, really boosts your prestige scores. Yeah, that's something which I won't cover, but there are ways to test those inflection points called segmented regression and breakpoint analysis. Now we can also get 4 diagnostic plots directly from the model you've just run, and that's simply by using the plot command. So you remember that we made this model education, and if you don't put in which, it will print all 4 at once, but I've put in which to sort of print them sequentially so we can evaluate them step by step. So this is looking at the linearity, and we're hoping for sort of a straight line and not an entire parabola. So it is somewhat of a thing, but this is, compared to this line, it's not doing too bad, in the sense we don't have an entire U-shape or an entire zigzag type of shape. So it is fairly linear, we would say, yeah. And again, you can sort of see what's going on here. It's probably because something is happening along these lines that we don't get this perfect type of mapping here. So that's the first plot which we would get if we do that. The second plot, so this is the normal distribution of the errors. And in a perfect world, all those points would lie on the line. Yeah. And so we see some deviations for newsboys at the bottom, whatever those might be, and some deviation at the top. But it doesn't stray too much from the line. And also importantly, where it strays somewhat at the bottom and somewhat at the end. So it's not like veering off entirely, like going like this, showing that we make that there's lots of it that's really skewing the distribution of errors. So it's by and large, again, fine, I would say, in the sense that we're hoping that the central limit theorem helps us out here again, and it could have been closer to the line, but it's not as bad in terms of programmatic. And so you can interpret these as z-scores, right? Because they're standardized. So three standard deviations away, 2 standard deviations away. And so at the extremes, it's not all that surprising. At the extremes, our predictions become worse because we're trying to estimate using the extreme of the cases. Everybody with me? So we want them to be on the line. By and large, I would say okay. So this is a plot which would help us to look at the homogeneity of our variance. It's slightly more complex to look at, but what we basically want to see here is we don't want to see a funnel. So we don't want to see this going broader like this or broader like this. So we want the points to be roughly equally spread across the line. And by and large, I don't really see a funnel going in this way or a funnel going in the other way. So by and large, the points are roughly equally spread across the red line. And it's not like for the fitted values here, it's widening as opposed to here. It's roughly, it's not too bad. Yeah? Everybody understands? So you can again read more about what it's doing, but this is mostly how you interpret the plot. So you don't want any funnels in this plot. You want things to be symmetrical across this fitted line. And otherwise you're over or underestimating the errors. And there are ways to correct for that, and I'll come to that later. And then finally, you might have heard of Cook's distance, or D of beta, you might have heard of also, and there are cases which could be potentially very influential outliers in your regression analysis. And this plot nicely shows you which cases are potentially outliers. So perhaps farmers are outliers, newsboys and physicians. So perhaps you can, it's sort of, there's different rules. So some people say you could use this in terms of values and calculate some formula in order to say these are clear outliers. Mostly I would recommend that you just do it graphically. And if things are outliers, you could consider running your analysis with and without farmers and seeing if you get the same results. If you don't, then you know something is really off with the farmers. Yeah. So rather than just deleting them altogether, I think it's usually good practice to present both with and without outliers and to see what the results are like. And again, perhaps these two shouldn't be that big outliers because there's some other peaks which are also quite close by. What is really worrisome is if you have one really giant peak here and all the other needles being flat, that points to the fact that there might be some issues. But this tells us that the influential case might be farmers. So the remedy in that case would be to, so that would violate the issue in terms of normality and linearity distribution. So you then run your analysis again with and without farmers, or you would use something like bootstrapping, where we sample a whole lot of times from the same distribution, and this outlier will have a lot less weight than when we just do it once. Yeah? So those are the 4 plots which you will get. I would recommend whenever you run a regression, you look at those plots to see if nothing quirky is going on, and what happens. Can't we just use ggplot and make scatter plots? For some things, you can, like in the beginning I've shown you, that it's quite good practice to first look at the baseline relationship, but for more complex things like homogeneity variance, you won't be able to do it, especially if you have multiple categorical variables. So really rely on the plot residual thing there. There are ways to get ggplot to make really pretty, make prettier than those things, but for your diagnostic purposes, those plots are sufficient. Yeah. Some of these plots will give you information which you would not easily derive from a scatter plot, especially if you have 3 or 4 variables. So currently we have a very simple case, which is 1 predictor, but if you add more and more cases, it will become more and more complex. So don't just do that. So we can also test homoscedasticity via something called the Breusch-Pagan test, which is you might not have heard of because it's very popular in econometrics, but not necessarily in psychology. This is a well-established test. And we need to package Imtest to do that. It's BP test from Breusch-Pagan. The model we want to evaluate, that's all we need, and then we'll print some type of output. And the key thing here is the p-value, and as we saw in the graph, there wasn't really a funnel present, and it's also this Breusch-Pagan test says we shouldn't really worry about violations in terms of homoscedasticity. Yeah? So it's not heteroscedastic. So homoscedasticity is the assumption. Heteroscedasticity is what you get if it goes wrong. Any questions? So that's just a test which you can do in case you really are a little bit confused about the plots. You can also rely on that test. And then autocorrelation, which is one thing which we haven't covered thus far, for which we had no real plots. We can test by the Durbin-Watson test. And in this case, we would find that there is autocorrelation. So that means that there's some suggestion that things are correlating by itself in the data, which shouldn't happen, because that's the assumption is that everything is independently observed, and there could be all sorts of reasons, because, for example, they sampled it in a certain way, or there's the same people rating the same individuals. There's some residual autocorrelation in the data, and that's a problem for our estimates. Yeah? So autocorrelation just means things start correlating by themselves, and that's a problem. And they could correlate, for example, by themselves. If you think in terms of countries, for example, spatially, like Germany is closer to Austria, and if we don't account for that, then we'll have autocorrelation between 2 variables, let's say meat consumption and GDP, and it has nothing to do with there being a relationship, but it has everything to do with the fact that Germany is closer to Austria than it is to Japan. And similar countries will behave in a similar way. So that's an example of spatial autocorrelation. Another thing would be temporal autocorrelation, so things which are measured in the same time will start relating to itself, even though there's no real relationship. And if you don't account for that, you would say, aha, there's a relationship between number of guns sold and homicides. Now in this case, there is a real relationship, but they start correlating by themselves just because you measure them over time. And things over time will tend to correlate with one another. Okay? So the alternative to the Durbin-Watson test is the box test, and in this case you get the same type of I'm just telling you this test, probably your supervisor will never have heard of it, but it's a good test to know if you ever work with longitudinal data, because this is the type of test you will have to do to check if there's still trends present in your temporal data. That's called a box test. And again, it's part of this, I think it's part of the LM package. We would have to call the residuals. And what we test here is if there's any type of trends present in the residuals by the box test. So residuals, model educations, and again, think of the residuals as sort of a trash bag. And ideally, if we had a perfect model, there should be no patterns in our trash bag. And if there are patterns in our trash bag, then we have problems. Yeah? Because that means also we're making problems and we're making mistakes in how we're estimating our models. So it's a chi-squared value, degrees of freedom, and a p-value, and in this case it corroborates what we found from the Durbin-Watson test, that there is an issue with autocorrelation in these data. Write-up. So usually it's good practice to describe that you've tested your assumptions, and so a sample write-up in this case would be visual inspection suggested that a linear fit was appropriate. That's what we saw with this graph. Visual inspection also suggested that the errors from the OLS regression model were approximately normally distributed. That was that QQ plot. A Breusch-Pagan test, you could also again say a visual test suggested that there was an issue with that there was no issue with homoscedasticity, but in this case I've just written the Breusch-Pagan test. So a Breusch-Pagan test showed that the assumption of homoscedasticity could be upheld because it's not significant. And I put in the chi-square value and a p-value. Yeah. And then, however, a Durbin-Watson test indicated the assumption of independence of errors was violated. And then Durbin-Watson test value and a p-value. So for some things there will be A-to-A things, but for example, Durbin-Watson, as far as I'm aware, there's no standard, so you just put Durbin-Watson. But if something is clearly a chi-square distribution or a z distribution, and it's a widely used test, then perhaps you can put chi-square or z or t. Yeah? So problems. Now we've got problems. So linearity. In that case, when we have linearity, as I've been telling you, you can transform the data. Think back of log transformations. So if we have an exponential function, making a log transform will make it linear. So if we have something which goes up and up and up and takes a huge rush forward, then we can log transform that to make it linear. Yeah. So if we have an exponential growth, for example, of a tumor, we can make that linear by taking the log transform, and we can take the exponential function to then interpret what it would be. Yeah. So the exponential function goes a little bit like that. Yeah. You can fit different curves in case that doesn't work. So you can try cubic functions or other functions in case it's not linear. Again, with normality, you can try and transform the data to see if it solves it in some way, to see if you can get those errors, which there might be a skew in. If you take the square root, they might become more linear. So you could try a couple of things where you transform your dependent variable to see if it will make it more linear. Heteroscedasticity, there's something delicious called the sandwich package, and that does errors which will correct for this. So basically your coefficients, your b's will be the same, but it will correct. So as I said, with heteroscedasticity, we're over or underestimating those errors. It will adjust those errors so we get the correct errors. So that's what it does. It's a little bit beyond this, but I'll give you some examples and towards the end perhaps on how you would do that. Autocorrelation. Sandwich package can also calculate autocorrelation corrected errors, which will take into account if there's a trend in your data which there shouldn't be. And so it can actually do both. So it can do heteroscedasticity, autocorrelation consistent errors. And there's some other ways of doing this, and that would be penalized linear regression or a different type of estimators. Again, this goes a little bit beyond this, but you should know that these solutions exist in case you run into problems, and then you can find out what you could do in case you have them. Also for your, you can read the exercise and read more about the packages. So now we've got problems, and I've given you some tips as to how to avoid them. Now often you won't just run one regression, but you will run a series of regression, and you will have hierarchical regression models. Yeah? In principle, you should run your checks for every single model in between, but sometimes people only do it for the last model. So, but often we want to build a table. So in step 1 we add education, in step 2 we add income, in step 3 we add gender, and then we see, for example, if the effect of education stays after we control for these variables. Yeah. So in this case, we've added women to the test to see if that effect of education stays, and then in this case we find it's still significant, and we also get a highly significant effect of the proportion of women in that sample. And so we can add things, and that will be the hierarchical part of the model. We're hoping also that as we go up, the R-square increases and we're explaining more and more variance. Or in the case of controlling, it's just we're not really interested in the R-square, we just want to see if this education effect, if that coefficient stays the same throughout or starts going all over the place. Because that probably means it's not a robust effect. It means that after we control for the amount of women, if the effect goes out of significance, then likely it's not a robust effect. Yeah? Then we have a scenario of where another effect is suppressing the original effect. So here you can actually see that it will print the R squared and an adjusted R squared, which you might also recall from SPSS in case you need those. I'm not a huge fan of those because they would also be very high if you just add junk to your model. So you can get very high R-squares, but it doesn't mean anything significant is happening. It just means you add a lot of trash to it. So it's a little bit worrying, and you can get F tests as you've seen below as well previously. Now our amazing package Stargazer will again help us to make really clean tables, and again this would be a time saver. So in this case, we call Stargazer. We have the module of education, the element of education women. I could have called it model education women, but I think I went for a little bit shorter thing here. Again, pick something. Doesn't really matter as long as you know where your objects are stored. These are the dependent variables labels. So we say it's prestige, and then this should be the sequence of the variables that we inputted in the hierarchical regression. So in step 1 we added education, and step 2 we added the percentage of women, and so those will be the labels which will then be printed. And then we can pick a style, and you should look again. Unfortunately, this one doesn't do APA tables, but it will do some very clean tables, which will take you minimal effort to make something nice out of it to report. So Demography or American Sociological Review or American Journal of Economics, or there's plenty of journal styles in there for which it will print really nice tables. And in this case, we also said we don't want a header, and you can add a header to it if you want to. So just to show you that it works, I'll just again exit this, and I'll see if I can show you. So hierarchical. What you then should get is something like this, like a nicely formatted table. So it will print it a constant here at the bottom, and it's put the key variables on top. So education year, so those are the labels we had. Model 1, Model 2, and quite interestingly, you can see that the coefficient sort of stays the same, remains highly significant. We also have a highly significant coefficient for women. And the things in between brackets are the standard errors from our model. And it's printed the adjusted R-square, the R-square, the N. It's used the star notation. It's printed all the F statistics. So again, this will reduce the likelihood that you make errors copying things from to Excel and then to your reports and everything. So sometimes it's just easiest to make a table, export it, and then refer back to the table. There will be no scope for mistakes that way, unless you make mistakes in your code, obviously. But copying or rounding errors, it will have done it all for you. Yeah? So hopefully more and more I'm trying to sell you on the idea that it's not all bad, and in the long run it will save you time because you don't have to mess around with Excel or copying and pasting between SPSS and Excel and Word. Okay, so you can look at the Stargazer package to see how you can further customize it. And I'll go back to the slides now. In case you're wondering, you can just so what I usually do is I take that HTML, I load it in the browser, and then I copy and paste that into my documents. Or you can use insert, and then you can insert HTML objects directly into Google Docs or Word, depending on which version you have, and then that will work in your report. But the easiest thing is usually to put it in the browser, Control A or Command A to get everything, Control C, Control V, copy paste. Okay, so that's what we did with Stargazer. And then in terms of write-up, you would say table X describes the hierarchical regression on prestige, and then the model showed, then you would describe what you would see in the table. So the model showed a statistically significant positive effect of years on education, of years of education on prestige. In the second model, the effect of education was upheld while controlling for participant A. It shouldn't be participant H, sorry. Something, it should be percentage of women. So I'll correct that. And the effect of women was also statistically significant. It's because I copied these from something else. I have standard write-up. So I'll correct that. But you get the gist. So you just refer to what you see in the table, and the reader can then reflect back to the table. So under APA rules, you would try not to duplicate and try to not put the same numbers which you have in the table also in the text. Especially if you have more complex models, it's best to build a table. Okay. Centering. So it can be hard to interpret those B's because they would start at a natural 0, or they would start somewhere where we don't want. So most of the time what we want to do is we want to center our variables because it will make it easier to interpret what's going on. And again, you should sort of know how you should do that. You've done that before, so you use the mutate command from dplyr, and then we make women-centered, which is women just minus the mean of women, education-centered, and then prestige-centered. And the reason we do that is because then when we have a B coefficient, it means a shift away from the mean in one direction or a shift away from the mean in the other direction. Otherwise, it's a shift from the 0 point of that variable, which might be quite odd because age starts with 6 and another one starts with something else. So we center everything in order to get more interpretable coefficients, and also you will have to center when you calculate interactions because it will make it easier to interpret interactions in terms of deviations from the mean. And we'll also avoid some issues which you might get with multicollinearity when you do interactions. So if you want to interpret those B's, sometimes it's easier to center them. And so what I then did is I built a centered model. So it's again the same, but now I've used the centered variables, which I've just built to analyze. And then we can use that centered model to see what would go on. And so we can see what our model would predict, for example, if people have 2 years more education. Yeah? So you can use that model to then look at actual predictions. So what we do is 3 years of X-ray education is 10.86, and that's just that number times 2. Yeah, rounded up. So if occasionally you'll be asked to make estimates for what happens if people's BMI shifts with 5 points, what happens if people's height shifts with 20 centimeters, and you can use the regression models after you've centered them to make those predictions. Everybody understands this principle? You've done that also perhaps for your undergraduates or degree or not. But the principle is just once we've centered everything, everything is around to mean, and then we can look at deviations away from the mean one way or another. That's not the same as z-scoring. Z-scoring we divide by the standard deviation, but it's that's the next bit from B to beta. So the B's are all unstandardized, and if in some cases we want to compare how much a unit of education weighs against a unit of gender or a unit of something else, and that's why we have betas. So you remember hopefully scale also from your package. Betas are nothing more than standardized regression coefficients. So it's basically scaling everything and dropping the intercept. And so you interpret them as a shift of one standard deviation away towards one end or not, or the other end. Yeah. So one z-score is a one standard deviation. So if a beta is 1, that means if you shift one standard deviation in x, you shift one standard deviation in predicted y. Yeah. So a beta 1 would be a very big effect, right? Because it would mean that they're nearly perfectly aligned. It means that if you move one with a factor 1 standard deviation, you move the other one with a factor standard deviation, which would be a dramatic effect. So we use -1 because we have to drop the intercept from the model. So you might remember that standardized regression goes through the origin, it goes through the 0. We no longer have, also when you print the SPSS tables, there is no value for intercept. So we have to tell R to lose the intercept. So we first do model education stand, and we can actually scale within the thing. So you can make new variables, but here I've just scaled it within the model. So I used LM, scale prestige, so make a z-score of prestige, make a z-score of education, and -1 to drop the intercept. And then I have to tell it where the data is. And so now we have betas. So this is now a beta, which is a larger effect, 0.85. And so that's how you get your betas, which you might also need. As always, there's other ways to do this. And one package does it quite handily, so you don't have to use this the scale command. It's QuantPsyc. So be wary that if you use this package or you use other things when you calculate betas for interaction effects, if you don't center things, things will become quite muddy quite quickly. So don't just rely on don't just blindly rely on packages to do that, but have a think about what it means in terms of a shift. So we currently don't have interaction models, but once you have interaction models, things become more complex for betas in terms of interpretation. But basically, we load the QuantPsyc package, and then we use lm.beta, and then it will print the beta, which we need for this. And it's the same as with one that we got here. Yeah. So, by now you should also be familiar with bootstrapping. You've done it a couple of times, perhaps in your assignments. I've been going on about it for quite a time. Again, you can bootstrap any statistic you find using the boot package. I won't run through it because it's exactly the same code as we send for the t-test and for the other tests. The only thing you should have to find out is which coefficient it should look for and where. So in this case, we tell it to go to the boot, find the coefficient of position 2. If we have multiple models and there was a variable at position 3, this would be 3, 4, etc. Because 1 is the intercept for an unstandardized model. That's why it's 2. Yeah. So that we can do that for any statistic, and then we can get basically. So this is the original B that we got, and then we can get the 95% confidence interval as we've done before for that B. We can say it will range from 4.85 to 5.97 with 10,000 bootstraps. So we have a range of uncertainty around it. And so the nice thing is, if you do bootstrapping, this is a non-parametric technique, so you don't have to worry much about linearity and all the other issues you came across, because it will repeatedly sample from the same data. It doesn't fix everything, because if you have autocorrelation, for example, it's still going to be autocorrelated because it's still sampling for the same thing. Same for some other issues. But it can deal with some of the normality issues or some of the effects of outliers. Everybody understands why you want to do this? Because it gives you a range of uncertainty for a coefficient. So basically, we just ask the computer to repeatedly sample and do the same thing over and over and evaluate those statistics. With me? Now, the last bit, which I hope to cover, is logistic regression. So sometimes you want to do a regression, but your dependent is dead or alive, or a man, woman, or something else, or it's a categorical, two-category variable. I won't talk to you about multinomial logistic regression or ordinal logistic regression, but they're expansions of logistic regression. And basically, the premise is that we want to apply the same techniques we had before, but now we can't really use them because we have something which has just like two values. So how do we get around that? So sometimes we have a dichotomous outcome. We have yes, no. The participants complete the questionnaire. Did they gain weight? Did they lose weight? Just a yes, no split. Or even more crude, did they survive the Titanic disaster, or did they die on the Titanic? That's one of the favorite examples. We can't use ordinally sparse regression because it violates the assumption of normality. Yeah. So because we now just have two values, and that messes everything up. But we can do a clever trick, and that's by relying into turning proportions into odds ratios. Again, if you don't follow this entirely, you can read about it in your own time. All you have to know is that this solves the problem we have, and it basically takes a proportion and we can convert it into something which looks linear. So suppose that you have yes and no, you can then have the proportion of people who respond yes, that's let's say 85%, 0.85, and the proportion of people that said no, 0.15. And those proportions we can convert into odds. We can divide one by the other, and we have the odds of a yes response versus the odds to a no response. Yeah. If you're a betting man, you all know about odds because Liverpool is 5-1 or Newcastle is 6-2. So that's the division of an event happening versus an event not happening. That's the basic way to explain odds. A horse will win the race or won't win the race. Newcastle will go into the second division or won't go into the second division. Those are odds. Those odds we can compare to one another and we can calculate ratios, so we can see if based on the response the odds increase or the odds decrease. So those are odds ratios. And those odds ratios we can convert into log. We can take the log of that, and that will be linear. And there's mathematical reasons why that's the case. I won't bore you with this, but this is how it works. You can read the references for a full explanation. Just in a very brief nutshell, that's what's behind it. So we take proportions, we turn them to odds into odds ratios, we take the logarithmic transform, and then we get something which looks like linear. So magic. Some type of magic. Now, some typical assumptions for OLS MANOVA do not apply because, again, it's a long story. but they're estimated in a different way. They're estimated via maximum likelihood and not via ordinary least squares. And that comes with all sorts of properties which are beneficial to us. There might still be some assumptions. For example, if you sampled everybody in schools in one classroom and then another classroom, they're non-independent data points and we're making errors. Again, if you apply a measure which has a measurement error to it, your logistic regression won't solve that. Yeah. So there are some issues with design which are inherent to any type of statistic you use. But it's, you need to have the correct coding of the dependent variable, so it has to be 1, 2. So if there's measurement error there, we're going to make a problem. So if we have, for example, if we're recording death of rats and one of our research assistants sleeps and misses recording, then it's not correctly coded, and then we have problems. All the relevant variables should be included, and there should be no under or overfitting of the model. So if you have all the relevant variables, then it will be the best possible model. But if we missed some, so for example, it turns out we should have measured people's blood pressure along the way, and we didn't, there's no way of recovering from that, and we're missing out on that. We're then misspecifying the model, perhaps. But again, you shouldn't just keep on adding junk, because you can just add junk and then the R-square will go up and the model fit will increase, but it's just learning on the noise. For example, you could add eye color, and if there's some really weak correlation, then over time we can get perhaps a model going which looks at eye color, but there's nothing in reality. It's just learning, or it's just modeling noise. Again, independent observations. This again ties into the issue of multicollinearity. Independent variables should not be too strongly correlated to one another. So if they correlate, let's say 0.8 or 0.9, then usually that's going to be a problem because one is nearly directly a function of the other. So in those cases, you would likely make a new scale out of it, or you would pick one or the other. But if you have very highly correlated independent variables, then that's going to be a problem for your model. And you now have to have linearity, but it's linearity between the log odds and the actual variable. So it still makes the linear assumption, but we don't care anymore about one variable versus the other. We care about the linearity of our log odds and the variable. So if something has an exponential relationship to it, then that might still be messed up. Or if you have a variable which is very skewed, like for example, 95% of your people will live and 5% die, then it's going to be very hard to get a log transformation going, which will be linear to that. But it's the linearity between the log odds and not between your dependent variable and the independent variable. You need a sample size. It's required for estimation. Again, it uses maximum likelihood estimation or restricted maximum likelihood estimation. Those methods tend to do quite well, but they tend to be biased for smaller samples. So for smaller samples, you sometimes will see that researchers use restricted maximum likelihood because it deals better with smaller samples. But according to some, you need 10 per independent variable. According to others, that are more conservative, you need around 30 per independent variable. So if you want to, let's say, if you want to model something and you have 10 independent variables, then you need 300 cases in order to model that. Yeah. Assumption checks. Some argue that actually you shouldn't even bother. You should just go ahead and do it because it's quite a robust technique. The opinions vary. Some people say you should. So some people say as long as you have a large enough sample and it's more or less linear in your head and it makes sense and you think you measured everything correctly, go ahead and do it. Other people say you should go and check, but it's a long story. But basically, the estimation method is different and it makes it more robust. That's why some people argue you shouldn't bother too much with checking all the 4 assumptions we did for for OLS regression as we did here. So some argue instead that you should think closely about sampling size and distributions at the design stage. Are you expecting it to be like a very lopsided, like 98-2 or something? Then this might not be the route forward before running the model. Again, you can always bootstrap. What I've shown you with regression also applies here. You can bootstrap everything. So I now have some other data, and there's no exercise, but if you have time, you can start working towards the exercise. The idea would be that you would start working on the exercise related to it, and I'll work you through an example of a logistic regression model. So this package MLbench contains the data. By now you should know that skipr allows you to look at the data, and it will show you, for example, how many of them are missing for every case. And we have data from Pima Indians on their diabetes developments, basically whether these women develop diabetes or not, based on how many pregnancies they've had, based on their blood pressure, based on some other measures. And that's a dichotomous measure. Yeah, so we want to find out if they are diabetic or not. That's why we use these data, and that's why we use regression. So how would you do a logistic regression? So the key difference here is you remember LM. This is GLM. So G is for generalized, and generalized is a different way of doing it. If you change the end stuff, which is binomial, which just means two outcomes, to Gaussian, then it will be a normal distribution. So it's a different way of estimating the models. And so if you want to do a logistic regression model, the code would be log1 GLM, our dependent variable, which is diabetes, our independent variable, which is here in mass, which is how heavy these women are in terms of BMI, the data where R has to look, and the family of the distribution, which we should have. Because this GLM can also do other sorts of distribution. It can do things you might not even heard of, like Weibull distributions, or gamma distributions, or all sorts of other complex distributions. That's why you have to specify which family you need at the end. And then it will print a summary, which looks surprisingly similar to what you've seen from regression. It will print an estimate, a standard error, a z value, and probability of the z value. So now we have Z scores rather than T scores. A long story, but it has to do with the generalized aspect to it. So everything is turned into a linear model. And again, these are the residuals, and if you're very clever, you can see whether there's patterns there or not. Okay, but bear in mind that this is now not directly interpretable. This is a log odds. So this is we've done some clever transformations to do that. So we can't really think of it as a B. It's a log odds of B. So that's log 2. So here we have age, and you can see that the effect of mass is still significant. And now also the effect of age. And again, it will print a formula which is run. Now, you can look at those as significance tests and see if your cases are significant. Those are known as wall tests or Z tests. But another way to do this is to use something called likelihood ratio tests. You should know about those. So summary gives you the parameter estimates and the associated commands, but you might also want to do a different type of test, and those are likelihood ratio tests. These tend to be better, especially if you have smaller samples. So suppose you are unlucky and you have only 15 cases per independent variable, you might want to use those instead of the sample estimates. You should be concerned if the conclusions from your likelihood ratio tests differ from the stars you saw in the significance test. How do you do it? You use the ANOVA command. So you do ANOVA, log1, test this chi-square, and what it will basically do is then test if the model becomes significantly worse or better when including the variable or not. And you can see some old familiar faces like the chi-square here, so it's significant. That's the same conclusion as we had with the parameter estimate, so in this case it's all good. Yeah. So this is a likelihood ratio test. And this is the same one for the other model, and you can actually see the p-values are quite similar to those that we had before. Everybody understands this? So it's just another type of test which has better properties for smaller samples. So it will test against the null model, which has nothing into it, and then it will start adding variables and see if the model improves. Now, odds ratios, I've talked to you about log odds, but we need odds ratios. So the coefficients that we saw in the output are not really interpretable, given that they are the linear relationship between the log odds and the independent variable and the dependent variable. So what we can do is take the exponential, and then they will become interpretable. Everybody knows what the exponential is? It's basically raising something to the power of something else. So, like a Big Bang Theory joke. So we can use a package to do that for us. Require odds ratio. And we can also then specify custom increments. So as before with regression, you might want to calculate what happens if people shift, let's say 5 units in BMI or 5 units in age, and we can see what happens to their the likelihood that they become diabetic. Again, you might want to center everything, which I haven't done, to make it even more interpretable. Say it's a shift 5 away from the mean versus a shift away from the absolute 0.2. Yeah. So we do not apply the oscillation package. The command is OR_GLM. We have to tell it which data to use. And then we have to list the increments we want to use. If you have categorical variables, there's no need to list increments, because it will. So if you just have male, female as an independent variable, there's no need to list them because there's only 2 values it can be. And then you have to tell the model it has to look for. So then we'll have done the odds ratio, the lowest confidence interval, and the highest confidence interval. So this means that with an increment of 5, the odds of becoming diabetic versus not diabetic increase with a factor 1.66. Yeah. So if you shift 5 units in BMI, the odds go up with as you would expect, with a factor of that in terms of 1.66. And we can put in any type of increment to calculate shifts. So you might want to put in a standard deviation, or you might want to put in 10 or 7 or 2, but we can use that for any type of things. And this is the same, but now we've looked at a shift of 1 in terms of year. So shifting 1 year, so older people are more likely to become diabetic, and it increases their odds with a factor this. And if you want to put 10, then you would see what a shift would be in terms of 10. So it's not just taking this value and multiplying it by 10, because it's the exponential transform of it. Yeah? Everybody sort of understands how this works, what the purpose is. So the coefficients are not directly interpretable, but we can calculate odds ratios, which tell us how much the odds increase or decrease as a function of a shift in the other variable. The alternative way of doing this is using the question R package. So as any type of thing in R, there are a gazillion ways to do it, and I'd like to tell you more than one way to do it, just in case you run into problems. And here we've done odds.ratio for lot 1, and it's printed this, but then it won't have calculated custom shifts. So this is just, if you shift 1 unit, that's what it would be, as you would have to multiply it by the factor in order to understand what's going on. So if you need specific estimates, I recommend that you use the other one. But if you just want to find out the overall odds ratios, they're printed here. And again, you get the confidence intervals and the significance. What does that mean? So in model 2, the odds of having diabetes, it should be having diabetes, not being diabetes. The odds of having diabetes versus not having diabetes is 1.11 times higher when BMI increases with 1 unit, while controlling for age. So all the other things in model are held constant. So if you have a model with several things in it, it's a shift in that variable while keeping everything else constant. Everybody understands the premise? So it's the same as regression. We've just done something funky to it. And you can use this to calculate specific proportions and predictions, because these are odds ratios, and you can calculate back to proportions. Because the odds ratios are a proportion of something happening versus a proportion of something not happening, divided by the proportion of something happening to something not happening. Because the odds is p over 1 minus p. So the odds of something happening versus something not happening. Okay, so you might also want an R-squared. Again, you might not always want those R-squareds. It's very complex, but you can get pseudo R-squared. So your actual R-squared doesn't exist anymore. It has to do with the fact that things are not linear anymore. But people have come up with all sorts of pseudo R-squareds. And this is how you get them. You use R companion and then Nagelkerke, which is one of the names of the R-squareds, and then it will print several of those R-squareds, which will give you an estimate of how much variance is explained. So think of them as your R-squareds, which you would get from regression. So sometimes your supervisor might ask you how much variance does it now explain. That's how you get those type of measures. So I have a couple more things to cover, but we'll see how we'll do it in terms of time. 1 or 2 more minutes, and then it's a lot to take in. Then you can practice on your own time and post questions in the discussion board. So the nice thing is, again, we can again use Stargazer to print tables for us with those odds ratios. So what's happened here is that you can also use tidy, as I've shown you before. You can use tidy and then broom to take values, put them together, and make a nice little table out of it and export it. You can also use Stargazer. But the key thing here is that we want to exponentially transform the coefficients so that their odds ratios are directly interpretable. So that's what I've added here. And I also want to switch off the t and p values, because otherwise they will be incorrectly calculated. They will be calculated based on the transformation or the raw coefficients. So usually we want to switch those off. We want to keep the star notation, but we don't want to keep the t values or p values. And so we tell it to report the variables and the constant and the star notation, and you can look at those different commands. And this is, again, just the style. So we don't want a constant. We're not interested in the constant. We just want the odds ratios. And we've put in some labels, BMI and age. So this will make a hierarchical table with odds ratios and our thing. So let's have a look at what that looks like. So it's printed those odds ratios with the star notation quite nicely. And again, BMI, age, log likelihood of the model, the AIC of the model, and the star notation for significance. So again, quite a nice overview table, which will tell you sort of what the effect is doing and where it's going. Yeah. So I'll just run you through how you would write it up, and then we would stop there, and the rest I'll put in the video. It won't be much longer. So table X shows the key result for a hierarchical logistic regression analysis. In model 1, there was a statistically significant effect of BMI on having diabetes. And then I reported a chi-square value, and that's the chi-square value of the likelihood ratio test. And I reported those here because they're not part of the table. Yeah, if you had put them in the table, then you could just leave them behind. But there's no test like this in the table. In model 2, there was a significant effect of age after accounting for BMI. And the chi-square values correspond to the likelihood ratio test, which you got from that table. And that's the deviance value from that table. And you can also calculate it for your model overall. And you might want to add that pseudo R squared, which I've shown you. And you would then go on to describe the odds ratios in terms of like a shift of 5 units means this, or a shift of 1 unit means this. So using that table or using some type of example to make it interpretable. Or you could illustrate the effect graphically. You could show what happens if people gain 5 units in weight, and then you could calculate the model predictions. So a lot of things to take in, but have some time reading through it. There's an exercise attached to it, and then I'll make a recording of the remainder. It's not that much more. It will be like 5 or 10 minutes or something. And any questions, post them on the Blackboard, and I'll keep on working on the assignments and on the exercises. Best of luck, and I'll see you next week.